Welcome to the lecture on different discretization schemes. So, in the last lecture we talked about the problems related to convection and diffusion and how to solve them, and we have so far used the central differencing scheme, because what we have seen is that we need to define the property at the control volume cell face, and there how to define that. Normally we take as the average of the values which is on the east and west side node, and that way we are calculating. Now, what we see normally when there will be convection dominated flow, in those cases it will be it will not give proper result if we are using those schemes. So, in fact, what happens that in such cases it will be more dependent upon the upwind node values. So, in the case of the flow direction, whenever there is a flow involved and flow direction is there, so this central differencing scheme does not do well. So, that even we can see we will see later on when we solve a problem based on that. Now, in this lecture we are going to have the discussion about the different differencing schemes or discretization schemes which is available for the prediction of the cell phase value when we have to calculate those values using the nodes which is towards east and west. So, normally the schemes which are used are the central differencing scheme, the upwind differencing scheme, hybrid differencing scheme, power law scheme. We will also discuss about the higher order schemes like quick scheme, and there are many more, but we will try to have the understanding of these schemes, because when we do the modeling of the fluid flow inside the TUNDIS, at that time in most of the modeling tools or maybe softwares if we use, we need to specify these schemes, and we must be acquainted with the effect what the different schemes will be generating, or which of the schemes are there which should not be used, because they will be having the problems while the convergence of the solution or so. So, we have talked about the central differencing scheme earlier, where we take the values that is based on the both the east and west nodal values. Then next comes is the upwind differencing scheme. Now, upwind differencing scheme basically it will be normally that when you have the flow direction. So, in case of flow direction, the central differencing scheme has the inability. Now, that is being taken care of when you have the chance to use the upwind differencing scheme. So, basically when if you look at, if you have the flow which is there, and which is if it is flowing in the positive direction. So, you have the velocity that is uw here at the cell face, and here you have the ue. Now, what we do normally in the case of upwind differencing scheme, or if it is also known as the donor cell differencing scheme. So, it will be taking into account the effect of this flow direction while we try to find the value at the cell face. So, the convected value at this cell face, that is your west cell face, it will be taken as the value equal to the upstream node value. So, normally in the case of upwind differencing scheme, you are when you are calculating the convected flux value, in that case at this phase it should be taken as the value at the immediate upstream node, that is your W. So, basically if you try to find the phi W, I mean that is at this phase, it will be equal to the upstream is this W node. So, you have west node. So, you will have it will be equal to west node value. Similarly, if we try to have the value of value at E. So, for E the upstream node is immediate upstream node is P. So, that is why you get the phi E as phi P, because this is the value, this is a node where, and anyway then you can have the expression in the form of phi P, phi W and phi E. So, accordingly you will have the A P phi P will be A phi E plus A W phi W plus S U, that is what we get that equation which needs to be solved. So, this way when you have a upwind differentiation scheme, you would get these values as this one and you get this value as this one, and then you get one equation, and if your stream is in this negative direction. So, anyway then you have to take this phi W. So, it will be, if you are having here. So, the upstream it is flowing in this direction. So, upstream is P. So, phi W will be phi at this P node. Similarly, phi E will be at phi capital E, that nodal value. So, this will be used to discretize the equation, and you get the expression for phi P in terms of phi E and phi W and the source term which needs to be solved, and then you get these values in terms of A P phi P, that will be equal to A W phi W plus A E phi. So, your central coefficient will be given by A W plus A E plus F E minus F W. Now, what we see that in the case of this upwind differentiation scheme, you get these values, you can have the idea about how that changes. So, what we saw is that you get when you have the flow in the positive x direction. So, your phi W, that becomes phi at W node. Similarly, you get phi E. So, you will have the upstream node that is P. So, you will have phi P. So, you will have, so what you can get the values. So, you will have F E phi E and phi E will be phi P. So, F E phi P. Similarly, you have F W phi W. So, phi W will be anyway phi at the W node. Now, that will be again you will have the d E and d W values. So, d E will be multiplied by phi E minus phi P, and then that will be d W multiplied by phi P minus phi W. So, that is what we normally get, and then if you try to solve. So, you can have the phi P terms on one side. So, if you take phi P terms on one side, so you will have this side it will be minus d, and this side it is minus d W is coming. So, and this side it is F P. So, that this will imply that if you take the d E and d W, and then you will have F E. So, that will be multiplied by phi P. So, that is the values here, and that will be equal to, then you have the phi E and the phi W term. So, you will have the phi E has here, if you look at the, you have the W term as the two terms. So, from here you get the dE phi E, and for W you get dW plus FW into phi W. So, that way you see that there will be change in the equation, so that you get it. Now, this will be further changed. So, that is what you get from here. So, what you see that this will be dW plus FW, and and similarly you will have the dE. So, that is when FW is more than 0 and FE is more than 0. When U is positive, in that case FW and FE will be, that is rho U. So, it will be positive, and that is why your AW will be dW plus FW. That is what you see, the AW will be dW plus FW. Similarly, AE will be dE, and then you will have the expression for AP. So, AP will be AW plus AE plus FE minus FW. That is what you get from here. So, and when you have the velocity in the opposite direction, in that case your upstream nodes are having different values, and in that case upstream your cell phase values will be different, because the upstream direction is now in the negative direction. So, for west it will be P, and for east it will be E. So, accordingly your expression changes, and that becomes again in that case it will be changing. So, you will have the different expression for that case. Now, this is how. So, in generalized way your neighboring coefficients you will be having the AW as dW plus maximum of FW to 0, and this will be D plus maximum 0 to minus FE, and that is how these differencing schemes are used for predicting. So, normally whenever you have these when the Peclet number is important, in those cases especially when the convection flow dominates, in those cases the Upwind differencing scheme is seen to work better. Now, the next scheme which is important is the hybrid differencing scheme, and this scheme is used when the central differencing scheme will be useful for the diffusional problems, when you have the diffusion dominant flow. So, in that case you take the central differencing. So, those central differencing schemes are useful, whereas when you have the convection dominated flow, so you take the upwind differencing scheme. So, that is because in the case of convection the upstream node square actually affects more than the downstream ones. So, in the case of hybrid differencing, what it takes is it will take the effect of it will take the advantage of both central differencing as well as the upwind differencing, and normally central differencing will be useful when your Peclet number is less. So, in those cases, and central differencing is basically second order accurate, whereas the upwind differencing is first order accurate. So, also it has the different traits. Now, in those cases what we is done is that this hybrid differencing scheme, it will be the using the piecewise formula and that will be based on the local Peclet number. So, local Peclet number will be computed, and based on that it will be using that piecewise formula for finding the net flux through that control volume phase. So, we know that this Peclet number is nothing but the ratio of F to D. So, you will have the so if you go to the hybrid hybrid differencing scheme, So, as we know that you have the definition of Peclet number at the west face, that will be F w by d w. So, you find rho u at the west face divided by tau west by delta x, and that will be w p. So, that is how you calculate these Peclet number at the west face. Now, what is done is that in the case of the the hybrid differentiation scheme, we find the net flux per unit area. So, net flux per unit area through west face. So, that will be computed using a formula, and that formula will be like you will have q w. So, that will be f w, and it will be multiplied by half of 1 plus 2 by Peclet number at the west. So, that will be multiplied with the phi w plus half of 1 minus 2 by Peclet number at the west, that will be phi p. So, basically, and when this Peclet number will be varying between minus 2 to 2. So, in fact, when the what we have seen earlier, that while discussing the boundedness criteria related to the differentiation schemes, that for ensuring the coefficients to be positive for AE, especially in that case, what we saw is that if the Peclet number is more than 2 or f by d ratio is more than 2, in that case A is likely to be negative. So, that is why when it is between minus 2 to plus 2, in that case it is taking the it is having the effect actually of both these phi w as well as phi p. So, that is why it is known as hybrid. It is taking the considerations for both these nodes in one case, and in other cases it will also change. So, for the value of from Peclet number from minus 2 to 2, in between you will have this one, because minus 2 means even if the flow direction is changing. So, in those cases your net flux per unit area through the west face can be calculated using that. Now, if your Peclet number will be more than 2, in that case, so if you see the convection dominance is more in the positive direction, in that case it will be switching over to the upwind mode, because in those cases the upwind differentiation schemes are said to be more stable or are more useful. So, in that case the q w, it will be f w, and phi will be at the w. So, that will be in the upstream node will be the western node, and if so it is for the Peclet number, the local Peclet number at this face, it is more than 2, and if it is Peclet number is less than less than 2 in fact. So, in that case what you see is that q w will be f w into phi p. So, that is the extreme node when we see the flow in the opposite direction. So, that way your f p will come. Now, we can have the values, these values putting into the discretized equation, and then we get the formula. So, what we get is that this central coefficient. So, A p A p phi p will be A w phi w plus A phi if we write. So, in that case you can have the A p as the A w plus A e plus F e minus F w, and for the hybrid differentiation schemes for steady one dimensional convection diffusion, neighboring coefficients can be written as the maximum of Fw to dw plus Fw by 2 and 0, similarly minus Fe and d minus Fe by 2. So, like that. So, basically so this is how in the case of hybrid differentiation scheme it will take into account both the things like central differentiation as well as upwind differentiation, and then accordingly it will try to the equations are solved and you can see the accuracy with respect to the exact solution, which we can verify in our coming lectures when we try to solve and learn it through by solving a problem. The other kind of differentiation scheme which is used is the power law scheme. So, this power law scheme, so it will be using certain power depending upon the Peclet number. So, in this case what you see that you see this Peclet number raised to the power 5. So, in this case depending upon the shell Peclet value, when it will be it will be exceeding 10. So, in those cases it is assumed that the diffusion is 0. So, diffusion will be set 0 and the flux will be calculated using a polynomial expression in this case. So, if you go to the power law scheme, so it is basically by suggested by Patankar. So, researcher, I mean there is a book also, a very renowned book by the author, that is S.V. Patankar. So, they have given the invention, done the invention of this scheme. So, what it tells that if it is the Peclet shell Peclet value is more than 10, in that case the diffusion is said to be 0, and when the shell Peclet value will be between 0 to 10, in that case the flux will be evaluated using a polynomial expression, and so in this case flux evaluated using polynomial expression, and if you try to find the net flux per unit area, so this one at the west control volume phase. So, that will be given by one polynomial expression, and QW will be phi FW multiplied by phi at the west node minus beta W, and this will be multiplied by phi P minus phi W. So, that is for the Peclet value when it is from 0 to 10. And if the Peclet number is more than 10, in that case it is considered to be purely diffusional. So, diffusion is said to be 0. So, that will be again going for the upwind differentiation. So, and in this case beta W, that is an expression, and that will be 1 minus 0.1 Peclet at the west face raised to the power. So, that will be all raised to the power 5 and divided by Peclet number. So, this is how it will be depending, and that is why it is known as a power law. And when your Peclet number will be more than 10, in that case the diffusion is assumed to be ceased, and then it will behave as the upwind differentiation scheme. So, in that case the QW that will be the FW times phi W. So, that is what is there for the the upwind differencing scheme where you have the upwind node is phi w. So, this is for Peclet number more than 10. So, this coefficient also in this case, as we see in this case, you have the central coefficient will be AW plus AE plus FE minus FW, and as we see based on this power law, we have the value for the AW and AE expressed in this form for the power law, power law schemes which are devised by the Patankar. And another scheme which is also used, that is the higher order scheme, and that is the quick scheme. Now, in this scheme basically what we do is that you have the two nodes on the two sides, and we also take one more node in the upstream side. So, if you have so in the case of the quick scheme, so in this case this is based on the quadratic form. So, that is quadratic upwind differencing scheme. So, in that case what we do is that you have this is your west face. So, this will be west node. So, in that case you take another that is WW, and this is W face, and this is your P. So, you are getting the flux value in the form of the values at the these three nodes in this quadratic upwind scheme. So, upwind differencing scheme. So, that is what is known as quick. Now, in this case if you look at the quadratic upwind scheme, if you try to understand, in this case basically the phi at the face, this is normally calculated in terms of 6 by 8 into phi at I minus 1 plus 3 by 8 into phi I, and then you will have the minus 1 by 8 phi I minus 2. So, this is if your this is I, and this will be I minus. So, this is I. So, in fact, this is the P point. This will be you are calculating that phase here, and this will be I, this will be I minus 1, and this will be I minus 2. So, basically you are calculating this 6 by 8 of this portion, 3 by 8 of this portion, and minus of 1 by 8 into this portion. So, that way you are getting. So, if you suppose you are trying to have the phi of the at the W phase. So, in that case 6 by 8 of phi W. So, from here I minus 1 will be here. So, that will be phi W. Then 3 by 8 I. So, it will be 3 by 8 of P, phi P, and 1 by 8 of the WW. So, this phase I minus 2 will be the WW. So, phi and WW is taken. So, this is how you calculate the values. This is for the west phase. Similarly, if you have the control volume at the east phase, so in that case you will have the values on this side also. So, on this side you have the east phase. So, your for this you will have P, W, and E will be coming out. So, your phi E, it will be 6 by 8 of phi at P node plus 3 by 8 of phi at E node, and then minus 1 by 8 of phi of W node. So, this is also this is a higher order type of differencing scheme, which is also used in many cases, and in this case the Never coefficient will be, as you see, it will be in terms of A WW also and AE also, depending upon where you are trying to find, and accordingly you will have AW and AWW AE and AE, how you find it. So, that is how it is computed in such cases. So, this is these are the in just we are having these different types of schemes. Apart from that, we have also other schemes like TVD schemes are there, so there are many other schemes also which you may come across while dealing with these studies, and typically in the softwares you will be having the mention, and basic idea is that you must have the understanding about how these schemes work, what are the fundamentals of these schemes and how they are used for discretization. So, that is what about the different discretization schemes. We will discuss about their performance by considering an example in our coming lecture. Thank you very much.